Hello there, and welcome to EE 386, the Intro to Controls and Robotic Systems. This course is taught through UAH's Electrical Engineering Department, and as I'm sure you're probably aware, for summer 2020, this is a remote course. This might actually work out in your advantage because it will be taught very similarly, the entire course that is, to office hours. A lot of students really tend to like the office hours format. It's one-on-one, and so we'll see how it goes. So what we're going to do in this first lecture video is first go through what you'll need to know about the course, the syllabus, the grading, all of that, and then we'll get into definitions and major concepts that you'll need to know for this course. So the very first thing that you'll need to know is Canvas. So make sure that you can log into Canvas. So if you're viewing this, you're probably already there. But from Canvas, our course will be labeled EE386, of course, and it'll have the short circuit Johnny 5 icon. I thought that was very appropriate for a robotics course. Okay, there are a selection of pages that you'll need to know about. The announcements is very important. I like to release a lot of information through announcements. I like to make updates through them. So of course, make sure that you can see them. When you log into Canvas, an announcement that you haven't seen should show up at the very top of the page. But make sure that you always check these and check them frequently. We have pages. I will add to these as the course goes on, but for right now, at the very beginning of the course, you should see the syllabus, a directions page on how to get the UAH MATLAB license to install, and a few other selected pages, kind of an intro page to the course and so forth. We also have a few other pages in Canvas, the files. I'll upload assignments through here and also occasional notes or handout pages. Also, the solutions will be released through here. So a homework solution or a quiz solution, you'll look into the files section and then into the appropriate folder. Your tests and quizzes will both come from the quizzes module. Your grades will be in the grades page, of course, and Panopto will hold all of our lecture videos. So I will probably release the lecture videos both on Panopto, up on Canvas, and also on YouTube. I like to upload on YouTube as well, and I have several things there as well that I'll reference later on. Okay, we were highly encouraged to use the module format, so our home page will show modules. A module is equivalent to a week in this course. So for the first week, we have this intro lecture and the introduction to the course, that kind of stuff, installation of MATLAB and so forth. A lecture, normally in the format, will be about 2 hours. That was our time slot. And so expect the lecture videos to be somewhere around that. I might split them up at some point. Okay, so let's go ahead and go through the syllabus. All right, so the syllabus for this course for the summer, just generally, you can view this under pages or you can go to the syllabus section under our course on Canvas. The format's online, so we don't have a dedicated time, and really you can view the lecture videos however you want at your convenience through the week. As long as you get your assignments done on time, then everything's good. Okay, so the best way to contact me if you have a question or you want to arrange office hours or anything like that is to use my UH email address. It is hunta@uah.edu. And of course, my name, because I've forgotten to say it already, is Ashley Hunt. And I'll go through a little bit of background about me later on. The course description here, basic theories about control systems. We're studying linear control in this course, and so we're going to really study techniques about designing linear control systems, feedback systems, Stability criteria, of course, different kinds of methods for that. Some frequency analysis, some just pure differential equations. Our prerequisites for this course are EE 382 and CPE 381. Either one of those is good. I would say coming into this course, the things you really need to know have to do with differential equations, a little bit of linear algebra, and be able to work with systems of equations. We do a lot of algebra. We do reference ODEs a lot in the very beginning especially. So if you brush up on those things, if you're a little weak on them, you'll be good to go. Our required text is the Modern Control Systems by Dorff. You can use any version of this textbook. It is right here. Any version of this. I have version 13, but really any version will work. We all have the tables, Laplace transforms, the I to E table. Those are the important things that we'll reference, and usually I will make a reference to a few homework problems out here, particularly in the beginning of the course, and I will always screenshot those when I do so. So if you have a different version, don't feel like you are missing out on anything. Okay, so that's the only required text for this course, but since we are doing this remotely, you won't have access to the UAH lab. You will need a computer that you have the ability to install software on. So any OS is okay. MATLAB works on Linux, it works on Mac, and it works of course on Windows. So make sure you have access to any computer. If you're viewing this right now, you have access to a computer, but make sure that you have access to either install MATLAB or access to something that MATLAB is already installed on. The student version is completely fine for what we're using, and you actually don't even have to have the most current version. I would recommend, if you have the ability to get the most current version, since you're a UH student, you're viewing this course, then installing the UAH licensed version, the student version of that, you should be able to get the 2020A version, no problem. That is the latest version at the time of this recording. That would be great. In general, always use the version that's newest of MATLAB if you can. But if you have something that's like 2012 even, that's still okay. That'll still work. As long as you have Simulink installed, that is essential for this course. So the only things out of MATLAB, and I detail this more on the page for the installation, install MATLAB and make sure you check the Simulink box if you are installing a fresh install. Okay, all right. UH does give students that are enrolled a free student license. I have directions on Canvas on how to download that or how to access the license key. And then you can go to MathWorks, use your UAH ID, sign in, install it, and go from there. The other thing that you need as far as tech is concerned is, of course, a phone or a scanner, some way to photograph your work and then send it to me. So this is essential for homework. And also, you will need to make lab reports. I'll call them lab reports here, but it's really a report from your simulation. So really with the sim assignments. And we'll go into that a little more as we go on. All right, so let's talk about the grading. That's the next section. So the printout is kind of messed up, the tab, but we'll go from there. All right, so quizzes. I've lowered this from my normal standard because we are remote. I feel like this is just fine. So quizzes will come from anything in the lecture. So if you're watching this right now and you pay attention, then you are set for quizzes. They require a little bit of thought, but it's usually somewhere in the neighborhood of 1 to 6 questions, something like that. It'll only take a few minutes. It'll be done through Canvas. So we will have 1 per week. Homework. We also do about 1 per week. This is a handful of problems. It's nothing too time consuming, but it should be enough to exercise what we go through in the lecture. So this first week, I'm not assigning any homework, but we are going to go through a little bit of the concepts that we'll use in homework set number 1. Your first homework set will be due June 8th, and that is a Monday. In general, quizzes and homework are due on Mondays, and also sim assignments, which we're about to talk about. So MATLAB sim assignments, this will be done through MATLAB Simulink, and then you'll build a circuit. You'll do all of the experimentation that I have in an assignment sheet and design any control that's necessary, do any calculations, assemble all of the answers, all of your work, all of your plots in a lab report, and we will talk a bit more about that in the next lecture. Altogether, quizzes are 5%, homework is 20%, MATLAB assignments, of which there will be 3 this semester, is worth 15%, and then we have a midterm and a final. The midterm date is around 7/1, so that's July 1st, and the final will be due on 7/29, so July 29th. So this is a very short semester, being the summer. It's about 10 weeks. So what I'm going to do for the midterm and the final, since this worked pretty well at the second half of last semester, we were remote, I am going to release these probably about a day early and assemble them like a take-home test. And you can work them. They'll be timed, of course. You'll have to submit your answers within a certain period of time, but you can work on them and pick when you start your clock and work on these. So, and the questions from midterm and final will, of course, come from homework and quizzes and lecture. So no surprises, really. We stick to the course material. There are a few critical thinking questions I like to throw in, but it's nothing off the wall. So, okay, so the course objectives for this, we'll just go through this real quick. Be able to solve control problems, be able to design controls, be able to identify the problems and the characteristics of the problem, and then be able to use the tools that we've gone through in the class and formulate the problems and the solutions to them. Okay, quick overview of the topics we're going to cover. So, of course, this first lecture, we're going through the syllabus and such, but we'll get into system concepts and a brief review of linear differential equations and all of that. Next, we'll deal with system behaviors, modification using feedback control, the design, canonical forms, linear dynamical systems, characteristics, stability. We'll deal with math flow diagrams and nested integration, not necessarily in all of this order, but these are what we'll cover this semester. Stabilization, closed loop stability, problem of insufficient outputs, design of transfer function controls, modeling of systems with the transfer functions, and design of the compensators, root locus, Bode plots, Bode techniques, and Nyquist stability. And we really end after Nyquist stability. That's about our last topic. Okay, I have our original class dates listed on here as well, and the final exam due date. Okay, the next portion, I try to describe each part of the assignments and everything. So you must be aware of Canvas announcements. That's a repeat of what I said earlier. Make sure you can see those announcements. Make sure you have access to a computer. Of course, if you're viewing this, of course you do. Have access to MATLAB Simulink. The latest is preferred, but even as old as 2012 is still okay, as long as you have both the Simulink and MATLAB portion installed correctly. And then, of course, have access to a scanner or phone. That's required for every homework assignment. Okay. All right, so questions and contact. Email is the very best way to get in contact with me. We can arrange Zoom meetings if you like, a voice and video kind of meeting. That's totally fine. And I'll try my best to stick to whatever's convenient for you, but letting me know sooner is, of course, better. From the time that homework becomes available to the time that it is due, you'll always have about a week, maybe a little bit longer, to do it. Usually longer for sim assignments. You always have about at least 2 weeks to do those. So if you have questions, let me know as soon as possible, and I will usually respond to email within 24 hours, often it's sooner than that. I do get Canvas messages, but email is much better. I can see that much sooner. Okay, so we were required to list Netiquette requirements, so just, this is common sense, I think. Don't type in all caps, don't use sarcasm. Please include your name at the end of the email like you would normally signing an email. This is really because UH email doesn't automatically set the display name for everyone all the time. Run into cases where I really don't know the student who's sending the email and I have to look it up, so that just saves me some time if you say your name. Spell out words and Y-O-U instead of you, things like that, as you would in a college course. Okay, so general policies. Don't cheat, don't copy. Every quiz, every test, midterm, all of that will always have an acknowledged statement that you are adhering to academic honesty at the very beginning of whatever test or quiz it is. So that's really you promising that you're not cheating, that you're not helping anyone else for that assignment. Now, there are things that it's okay to work together for, but quizzes and tests, of course, no, don't do that. All right, so next thing, if for some reason that you have trouble submitting your work through Canvas, I'll have a Dropbox for a test where you have to scan your work, and the last question will be where you upload that work. If you have any problems, you can always email me your work, and I will get it that way. If you do send it, I'll try and send you a response and say, yes, I have it, so you know, and you can de-stress. Grades will always be provided within about 1 week. I'll try very hard to adhere to that. Feedback for items such as midterms and final exam will also be provided through Canvas. So I will go through your problems as I'm grading them, and if I feel like it's necessary to write a note to you or point out something, I'll do that. And I upload a PDF file to the grades for the midterm and the final with that information. And of course, if you do something completely right, there won't be a note by it, but you'll be able to see how many points you earned, how many points it was worth for every question. Okay, assignment due dates will always be at the very top right corner of the assignment. There shouldn't be any discrepancy about that. I'll also list that on the pages, the schedule for our course. Okay, all right, so let's talk about the assignments now. Homework. We will, of course, have to scan homework. You'll be working things out by hand. You'll have to take a photograph or scan it and send it in. You'll submit that through Canvas. There will be a Dropbox for every assignment, and if for any reason you have trouble using that, you'll just send it to me by email, but this should work. Okay, work that is partially or completely unreadable will lose points. I'm sorry I have to do that, but it's up to you to make sure that when you photograph or scan your work that it's readable. Otherwise, I can't grade it. All right, so all work must be shown. Steps are very important for this course. I would say steps are more important than the final answer in most cases. Work that's not shown, of course, will result in lost points. So for a homework problem, I'll have, let's say it's worth 5 points. Well, certain steps will be worth certain points in certain allocations for that. So to get all the points, you have to show all the work. And it'd be very similar to the lectures that we have in this class. Homework solutions are generally posted the day after the homework's due. So for that reason, I cannot accept late homework. It's a very special circumstance where I'll accept it. You essentially have to let me know ahead of time that you're, for some reason, not going to be able to submit it on time. And then I would say the delay is very little, probably a day or so, because this is a very short course. We have to keep on track for this, especially in a summer semester. Okay, once a solution is posted, of course, I'm not going to accept any late homework. Okay, so we're down here. Homework consists of few problems, typically 1 to 6. That's kind of a variable number. I do like to put different steps in the homework, so one problem, maybe one problem, but I might have 6 different parts to it. So yeah, this isn't something that will take you 3 days to solve. It will be straightforward, just like the lectures. I just want to make sure that you get practice working problems. Okay. Homework is due Mondays at noon. You can, of course, submit it sooner if you want to. It's due Mondays at noon following the week it's assigned. So this week we don't have any homework assigned. I will have homework set number 1 available if you want to look ahead and start working on it. That's fine. But yeah, our first homework set is, of course, due June 8th. Okay. It should be submitted through the Canvas submission box, as I mentioned earlier, for that particular assignment. So homework 1 will go in the homework 1 submission box. This is generally 1 week from when the assignment's made available. That's so that you have ample time to submit your questions. There will be a total of about 8 homework assignments, somewhere around that. We will also have 7 quizzes for this course. Quizzes come straight from the lectures. They're very short. It's somewhere around, I put 5 to 20 minutes, but I really don't think it'll take you very long to complete those. If you watch the lecture, you'll know what you're looking for. You'll know the answers. If a scanned work is required for a quiz, then you'll have to submit that just like in a test in the last box of the quiz. They will be timed, but you should have enough time to do all of that. Quizzes will be available for 1 week. So in a given week, we will have a quiz. It'll become available on Monday, and it is due the following Monday. The due date will always be listed in the quiz description. So when you click quizzes on Canvas, you'll see how long you have to do that quiz. And if it requires a scan, I'll write that in there as well. And the due by date will be on there as well. Okay. All right. The last kind of assignment that we have are the sim assignments. There will be 3, as I said before. You must have access to a computer and MATLAB Simulink for this course. So I have a Canvas page for how to get the UH license, as I mentioned before, so you want to look at that. Any version 2012 or later is fine, as long as you have Simulink installed. We have an electronic document, so you'll want to assemble your work and everything like that. And of course, more instructions on this will come when I make that first Simulink assignment available. Start the simulation as early as possible. And I would say this week, if you get a chance, go ahead and install it. It would be great if you could get that done this week. If you haven't already, click Simulink and start looking into that and just kind of get oriented. And then that'll set you up for success with this. I do have a few old videos. So back when this course was called 425, this course had a presentation that I made for the Professor Dr. Johnson, who was teaching back then. And this will walk you through Simulink. Now the version is a little older. I believe it is 2012 that I'm using at that time in the videos, but the concepts are the same, the settings are the same. So this is very helpful. If you go to youtube.com/AshSimulink, it's ASH, the first 3 letters of my name, Simulink, all one word. And then the YouTube course, or the YouTube playlist. Okay. All right, finally, the midterm and final exam. Okay, midterm and final will be listed under the quizzes module in Canvas. Test questions for both of these come directly from the lecture. They are comprehensive up to that point. So midterm will take the first half of the course. The final will take the entire course. All material for the final. Okay. Before each of these tests, I will provide you a list of review topics so you can go through it and check and make sure you understand everything on there. The questions are, of course, similar to the homework and quizzes and example problems that we work through the lecture videos. You'll also be required to scan or photograph your work, and both will be time limited. They are formatted to be about 2 to 2.5 hours, but that's actively working time. So in the class, that's what you would get. You would get 2.5 hours for a final, and I would probably give you an extra 15 minutes to 20 minutes or so for the midterm as well, if you needed it. But since we are remote, you get a little bit of extra time so you can go through and check your work. So what I want to avoid is when you look at the midterm or the final exam and the description, you're about to take that quiz, and you see that you have, say, I haven't quite decided the time limit yet, but say it's like 4 hours. Don't get scared. You don't have to take that whole 4 hours. It's not required. It is just so that if something bad goes wrong, if you have a power outage, something like that, you're not completely doomed. Everything's going to be okay. Of course, in that case, if you could contact me immediately, something's wrong, we'll do something for that, as in like reset your test. But let's hope that doesn't happen to anybody this semester. Hopefully not. So each question, each student has unique questions. So I like to have equivalent questions, but not same questions. That does help me prevent anyone from helping each other. Of course, I'm sure everyone in this class will adhere to the academic honesty, but do you know that you're not able to actually work together for this? Your questions will be different, your numbers will be different, and your graphs will be different. So, but you have equal difficulty. Okay, that all said, we will go through the introduction to this course. So of course, we've gone through the Canvas course navigation. So the syllabus, now we know the pages that we need to follow, and then also where the lectures are found under Panopo. I will also, of course, add them into the modules. So when you log in, your homepage will be modules for this course, and then the lecture videos should also show up under each module that they're relevant to. So make sure that you install MATLAB with the Simulink. Make sure, if you don't already have this installed, that you check out the UAH license page on our course here. And all right, so I also have a link to the privacy policy for MATLAB. That's a required thing. So a little bit about me, why I'm teaching this course, and so it's probably obvious already, but my name is Ashley Hunt. I've taught this course before, usually in person, at least halfway in person. Last semester I taught this course, and of course the whole pandemic thing, we were half remote, so a couple of lessons learned that way. Contact me by email. That's the best way to get in touch with me again. We can always do Zoom meetings for office hours. My degrees are in electrical engineering and applied mathematics, all from UH. I have 2 master's degrees, one in math and one in electrical engineering with an emphasis in controls. My thesis was also in this area in DC control. That is discrete continuous control. It's a really interesting area of control theory. And Dr. Johnson was my advisor, Dr. C.D. Johnson. You can find lots of papers by him. He was a very prolific writer in this area, and he actually came up with this area, and I was fortunate enough to work on it. So my 300+ page thesis is in this. I also work I don't teach full-time, I teach part-time, and I work in software development, which is completely different from this area, but it is really neat to actually use this sometimes. Every now and then you'll come across Kalman filters, something like that, and you can actually apply it. I help organize the local Python group, hsv.py. You can find us through meetup.com, and we do Python presentations in Huntsville. Let's see, what else? I work in modeling and simulation. I work for MTSI currently at a Parsons program. And I used to work for Northrop Grumman, again in modeling and simulation. So I also have several pet bunny rabbits. So if you have any experience with rabbits, we can probably talk about that. All right, so back to this course, and we will get started with the first couple of definitions and major concepts. So all right, so for this course, why is this important? What are we doing here? Well, we are going to be looking at linear control. So if we were to talk about control theory all together, it would be this whole big pile of different kinds of control, different kinds of problems, real world. So nonlinear control is really the real world problems. We don't deal with those. In this course, we are dealing with this subset called linear control. And if I were being realistic, I would probably make this bubble even smaller. Out of linear control, we are dealing with this very specialized form called linear time invariant, or LTI systems. That is linear time invariant. So these are really neat systems. They are very simple systems and really kind of don't exist in the real world most of the time. But they are homogeneous. We'll get into that, what that means in a little bit. You can use superposition. So if you've taken an electronics course, you know that you can turn off some of the problem, some of the circuit, and solve for values, work out issues in part of the circuit, and then turn it back on, kind of put it all together. That is a property of linear systems. And so linear independent systems, that is. And so we can use that property as well mathematically. Okay. And so this is where we are, and this is, you should probably label this nonlinear control. So you'll notice that nonlinear control is the entire bubble. Linear control is lying within the nonlinear bubble. So this is not linear. It's not necessarily linear. It's nonlinear. So these are captured within the nonlinear. Nonlinear is everything. Linear is a subset of that. LTI is a subset of that. Okay. All right. And as I said before, what do we really need to know within this course? Well, we are going to deal with matrices a little bit. We are going to deal with differential equations a lot. So if you like differential equations, you're in for a treat because we're going to be applying those. We do deal with calculus, a lot of algebra, and then also things like derivatives and integrals for the calculus portion. But sometimes we deal with things like partial fraction expansion, we deal with, for differential equations, ODEs. We don't really do anything too specialized, but general ODEs, we'll deal with those. And then basic physics, but really only with understanding problem scenarios. Okay, so I do need to mention the general UH policies. So remember that if you have a disability or need special accommodations, let me know. That is, if you have the paperwork and set up for needing extra time or anything like that on a test or quiz, let me know as soon as possible. I'd like for, in general, everybody to feel comfortable talking to me. I'm pretty easygoing, at least I like to think so. So please feel free to ask me questions whenever. And then make sure you can, of course, access your UH email for that. You will need it to get the MATLAB license. Okay, and then again, what is covered in this class? Well, first of all, we're going to be talking about a few definitions. Recognizing systems, how to formulate the problem, and then what are we actually solving for? What are we trying to do? What is a control? How to design one? And then modeling the systems with differential equations. Okay, so let's talk about where we are headed, and then we'll go through some definitions and some history of control and such. All right, so a control system will typically look like this. And you can see this in your textbook. They will have this same kind of picture. So we'll have a control box right here. We'll have it working on some kind of process. We'll have the system response out here. And then we'll have some kind of a measurement device. Okay, so this is symbolic. Don't worry about where the boxes are coming from just yet. But let me explain what these all are. And then the very first thing that we're going to have here is a desired response or a reference. Okay, so input is over here and output is over here. And then all of this stuff in the middle is what makes up our system. Okay, the system or environment, the thing that we are dealing with that we did not create, the scenario itself, say the stock market or a room's temperature, something like that. That is the process, and that can also be called the natural system. And we'll get through definitions in just a little bit where I'll write that out. But the process right here, this is the inherited thing right here. The control is typically something that we create, and we're trying to do something to modify this process some way. We are continually measuring what the system is doing. We're continually grabbing that output from that process, and we are measuring it here, and we are using that information within our control. Knowing the knowledge of what our reference input or desired response, whichever one it is, really they kind of mean the same thing. We're using that knowledge combined with what our system is doing to give information to our controller. So the controller is really made up of two parts: the control algorithm and the actuator. So the part we're going to really care about in this course is the control algorithm. That's the mathematical design. The actuator is typically the mechanical part that enacts what the control algorithm should be doing. So those together make up the controller. And the process, again, is our scenario or environment, whatever we seek to change, whatever our problem setup is. And then the measurement is something that we can get through a sensor. Some kind of a sensor. Okay, this setup right here is called feedback control, and this is what we will spend most of the course dealing with. I'll explain where that comes from and why we want to use this setup, but this is really the best kind of setup. You always want to have a negative feedback, and we'll explain why later on. But yeah, so if you think about it, having the input come in and not knowing what your system is doing already, well, it kind of makes sense conceptually, doesn't it? Where if you know your room is hot, you'll want to cool it. So you'll need that feedback, you'll need that knowledge. Okay? All right. So what is a control system in general? I've just shown you what it is, but let's talk about, with words, what it is. Okay, so what is control? Or we could phrase it more like, what is the presence of control? Okay, so essentially this is, and when I talk about this, by the way, I'm going to tell you in my own words, kind of explain it to you, you know, like we're sitting together, we're going through this course together, and we're just talking about it. But you can always reference the book definition. It'll be phrased differently, but the meaning will be the same. So essentially, what is a control? The control is kind of the interconnection of different components to kind of enact some change on a process, thereby getting a system response that you want, something you desire. So we are doing something to change the output of our process to be something that we want. Okay? All right, so that action is deliberate, it's intentional, and so let's write that down. So we are essentially changing the input of a system by way of some deliberate action. That action is actually the control algorithm to obtain a desired output. The important portions to note is that we are changing the input doing it deliberately or according to some algorithm in order to get a desired output. We are changing the input to that process. Okay, so if you have a system and you want the output to be a certain way based on a design, you have some constraints, you modify that system via the input so that you obtain that output. Okay, so this is really used in a lot of places. Some examples would include navigation systems. We have famous robots, something like Big Dog or Atlas or Spot. These are all robots designed by Boston Dynamics, and they have a really, really cool YouTube channel, so I would expect that you'll find some pretty good videos there. I will leave links to these. I usually show these in my class. They're pretty entertaining. Spot does a dance, Atlas does parkour, and then Big Dog can slide on ice. People kick it down, it gets back up. It's really cool. But yeah, I'll leave links to these guys on Canvas. So check out Canvas for that. We all like seeing robots, right? But yeah, navigation systems, planes, cars, thermostats, radar antenna, rockets, of course, any kind of missile guidance. We're in Huntsville, so we're all familiar with the DoD work here. Centered around rockets, space systems, all of that kind of stuff. All good examples of control. Okay, there are many examples in chapter 1, no matter what version you have of the textbook. There are lots of examples listed in there. They can date back to ancient times. There's an example that they talk about called the Greek water clock. Really, really cool. So, but moving on, we'll talk about systems now. So we have a control. That's what we're here for. Systems. Okay, so what is a system? Why do we model it? So a system is really the environment, the scenario, what we're interested in changing the status of. Basically, what we're interested in modifying the output of via the input. So that's the scenario or part of the environment. So some examples of a system would be the stock market or biological system like a cell. A cell could be considered the system, and then you have the different modules that live, I think they're called organelles that live inside the cell, and those have different functions which we can map to kind of like a control system. Also, businesses have different kind of business models, different ways of raising money, helicopter flight path, and say like we even have heavy winds or something coming in with that. That's the environment, and we kind of want to guide the helicopter through that. So we'd be using our control to do that. Or we take like maybe a fish tank, something like that, and we want to dispense food at a certain rate. And of course, we're doing that with a control system, but the fish tank itself, where the fish are living, that's the scenario, that's the environment. So that is our system. Okay, and so the system itself will contain different pieces. It'll contain it'll contain things like the processes. There might be more than one. It can contain our control, and it has an input and output. We might add sensors to it. Okay, so let's talk about components. So this term plant, this may not be one that you've heard before, but the plant is really equivalent to talking about the process. And again, a process is that part of the environment, something like that, that we can model. Okay, we've already mentioned an actuator. And so that language does come up quite a bit. An actuator is really the mechanical part, or the actuating part of the control. It is what enacts the control algorithm. Okay, all right, so a sensor. Pretty familiar with what a sensor is, just by definition. It will sense data and provide that as feedback. So essentially it just takes measurements. Let's say also it provides the data. We usually do that for the output, so we use that in the feedback. Okay, we know what inputs are and also outputs. That is the output of our system, that's an input to our system. But we also, to any typical box, if we were to talk about just our controller, that would also have an input and an output. The output of our control, and we'll talk a bit about symbols, but I'll go ahead and mention it here, we will symbolize with a U. U of t will be the output, that will be the control signal. The input to the control is typically a mix of the reference signal and the feedback. And we usually do that with a negative feedback. So I'm just going to go ahead and write that right here. So our reference input, if we were talking about right here, and then our feedback would come in right here, and then that together, and this is a summation block, by the way. It's probably pretty obvious, but we can write that with a summation sign right there. So it takes this input right here and subtracts off, if we have the minus sign right here, subtracts off the input right here. The summation of that is provided through this signal here. Okay. All right, so those are the main components that we'll talk about within our system. And of course, we already talked about the process, and we have a controller, and we have a sensor, and that's really the main parts. We also do have this portion that we'll talk about much later called disturbance. Disturbance is another input, and actually I'm going to talk about that. Okay, so we already talked about that our control signal is called U of t symbolically, and that is representative of the input that is desired. We design it to basically enact the control. So we're following our definition. That is the input that's desired to alter the output of the system, right? Okay. So, and it is by some deliberate action. Okay. Note that if we have no control action, this would be a 0. Now, I'll mention this much later, of course, but if we don't need a control, we do not have to supply one. Just keep that in mind. And so I was just talking about disturbance and just mentioned it. This is not anything that we are going to deal with right now, but I do want to mention it because we will be using it later. So what is a disturbance? This may be the first time you've ever heard this. Symbolically, we use W of it, and it is a function of time as well. This is something that is not controlled. It's typically not controllable, but we don't know what it is. So it's not known, not really knowable, at least not at the time we're viewing. Think of something like wind on a rocket, something that you have no control over. It may exist, it may not exist. A draft in a room, if we're thinking about a thermostat. So something that is an input to a system. It's very important that this is both an input to the system. It is not known, not measurable. And we have no control over it. We are going to discuss techniques in this class to accommodate disturbances, at least linear disturbances. There will be disturbances that we can't do anything about. And in those cases, you just kind of do the best job you can. But basically, these are the artifacts of what a disturbance is on the system. And in real life, these always exist. There's electrical noise in circuits, there's wind outside, there's weather, all kinds of things. So essentially, input to the system, not known, not knowable, at least at time t. Often parasitic. So often it's something that's working against us. It's pushing our system in a direction that we don't necessarily want it to. And then we have no control over it. So in real life, this is always a factor. So some examples of that, again, electrical noise, wind, radio static, interference, that kind of thing. Okay, so let's talk about the other symbols. I mentioned a reference input, and that's going to be lowercase r. That is our reference input. That was either a reference input or a desired output that we were supplying. So say we wanted our system or our temperature gauge. Let's say we're talking about a thermostat again. That's a really good example for this. We wanted the room to be set at 85 degrees, pretty warm. Actually, that's pretty warm. Let's make it 75 degrees, something reasonable. So it's 75 degrees. We are supplying that input. We are putting the setting gauge at 75 degrees so that the room will be that. That's really what I'm talking about as a desired input. So that's a reference right there. Okay, so that is the overall system reference input, overall input. It may be possible that we choose that, or we may be given it. Let's say overall system input. May be possible to choose. Okay, can be 0. It can also be a desired value. Okay, so next symbol, we are going to talk about the output. The output is typically y of t. Okay, so the system output will always appear at the rightmost side of the diagram. It will be symbolized by y of t again, and it's really the response signal of the entire system. It tells us the behavior of that system. We always want to measure this. So that's overall system output. And it shows the system behavior. So as we go and talk about modeling systems, a big factor will be if a system is stable or not. The first part of our course, we'll be dealing with stabilizing systems and talking about what is stability and how to get there, essentially. How to design a control to stabilize a system also right after that. And so it's really important to look at this y of t. So we're going to use the same symbol, y of t, on our system diagram up here. So this is our y of t right here. And then actually I'm going to flip back and label all of these, but we're going to use the same symbol in particular as we will for the solution to our ODEs, just to make it very clear these things are equivalent. Okay. So actually, yeah, it's a really good time to go ahead and flip back and let's label all of these. So here we have the control, and we said the output was our control signal. So there's our control signal. We already just labeled our system output, system response. System response and system output are the same thing. Let's go ahead and put that right here. Okay. Reference input, R of t, that is this line right here. That is either our desired response or reference input, and these two things could be exactly the same. Okay, and then our measurement signal, you see that this is coming from y, so really ideally this should still be y right out here. Our sensor hopefully shouldn't change the signal at all. And then we have, I think, everything here, but we don't have a disturbance coming in. So disturbance would actually be part of the process. So we might have a plant within the process, or plant right over here, but we would also have a disturbance coming in. In that case, I'm gonna write just this little summation. So U of t is now coming in here. Now don't worry too much about this right now. I just want to show you where this would go. This is where our disturbance would go. We don't control that. We don't have anything to do with it. It's just part of the system and we have to accept it for what it is. We do have to design our control to accommodate it if we can. If we can't, we just do the best we can. Okay, so there we are. All right, so I think that's about it for the definitions. Actually, you know what? We do need to talk about different types of systems since we're talking about LTI. All right, two more terms about that: autonomous and non-autonomous. Okay, so essentially an autonomous system is time independent. It does not have anything to do with time. It doesn't matter. As you increase time, the process might continue, but it would continue that way if it were today, tomorrow, next week, whenever. So essentially that's time independent as a process. So we talk about this phrasing like an autonomous system, okay, or a non-autonomous system. Okay, so of course, if autonomous is time independent, non-autonomous must be time dependent, right? Okay, so an example of this one is, say, like whether or not I mow my grass or what setting I have on my lawnmower depends on how tall my grass is, depends on the day of the week, the weather, and so forth. And of course, I can't mow my lawn if it's raining, so if it's raining tomorrow, I won't be able to do it then. That is a time-dependent, kind of environment-dependent situation, okay? And if I were to, say, like wind a clock and set that on the desk, that clock would not care if I did that today or tomorrow. It would tick the same kind of way. That would be more of an autonomous situation. Okay. I also have examples of the autonomous kind of robot. This is actually called an autonomata. I will also leave that in the Canvas links for this module. And these are really cool. I also usually show this on the first day of class. You wind them up. They were made by a clock maker over 100 years ago, and they will actually write, look like robots. They're a little bit creepy, really cool, good to see. That's a good example. All right, so if we were to talk about the type of systems that we're going to be dealing with, dynamic systems. The type of system that we can model with differential equations. Okay, so essentially a dynamic system reacts to an input. So if I change the input, the output is going to change. And so that, if knowing that, we can say that they are dynamic in nature. So we will be dealing with dynamic systems. We can model them with differential equations. If we need to, we can use Laplace transforms to kind of simplify analysis. We can use linearization if they're nonlinear and bring them to the linear side within a certain range. But yeah, so dynamic reacts to changes input, shows in the output. Okay, and of course, I'm going to go ahead and write this on here that we model with differential equations. I hope you like differential equations. We don't do anything too difficult in this course. I really liked that course in the math department. It was a lot of fun. It was probably my favorite math course, aside from metric spaces, which was just insanely hard, but still really interesting. Okay, two more definitions I want to walk through. The concept, actually these are more concepts. Open loop and closed loop. Actually, we're going to talk about this, and we're going to talk about single input and multiple input systems as well. Okay, these are more concepts than definitions, and I'm just going to want to talk through them. So we'll be dealing more with these later in the second half of the course, but a closed loop system is really one where we are dealing with the entire system. We are dealing with the overall output and the overall input. Okay, an open loop, we are dealing with a subset of that system. And we may have access to the overall input or the overall output, but we are really not considering some piece of that system, okay? When we deal with transfer functions, we will very often talk about the open loop transfer function of that system. And that behavior is not necessarily the same as the closed loop behavior. Okay, and that's really what you need to know for right now. I just kind of want to let you know, when you see these terms, what we are going to be dealing with the first half of the semester is really the closed loop altogether, and this open loop portion won't really come into play until the second half of the semester. Okay, and we'll go more into depth later. Okay, of course, single input systems and multiple output systems. So CISO stands for single input, single output. Okay. Mostly we will be dealing with CISO systems, but not necessarily. That is where we have just one input and just one output. You can easily have a MIMO system that is, of course, multiple input and multiple output. Okay, so an example of a CISO system, let's say I have a pinwheel. Let's say that kind of looks like a pinwheel a little bit. And we have wind that is blowing just this one direction. And so that means that the pinwheel rather, will rotate in just one direction. And there won't be anything like shaking or anything like that happens. So it's one direction and then one artifact, one output. One thing happens for an input and that produces one type of output. Okay, so we have a CISO system, and let's say I have this is the CISO system. Okay. All right, so now let's talk about an example of MIMO system. All right, for that same pinwheel, let me try and draw it again. I'm trying to make the leaves go kind of lean towards a direction like a pinwheel would, but there we are. Let's just pretend I did that, and made it. All right, so now I still have that wind blowing in that direction to turn the pinwheel, but let's say that I'm also shaking the pinwheel. So this little cap right here is not flush to the pinwheel, and the leaves on it, the wings, whatever they're called, they are also shaking as the wind's blowing, okay? So now we've got this kind of, if I'm shaking it back and forth, I'm going to probably get a harmonic kind of response that way, in addition to probably speeding up and slowing down the spinning here, and then I still have that wind. So two inputs. One is the wind, second is the shaking motion, and then two outputs that I can show, probably more that we can gather. One is the spinning, and the second is the rattling of these pinwheel flippers or wings or whatever we want to call them, the pedals, against that cap and the back of the stick that's holding them. Okay, so there will be two outputs as well. And that's just the first thing that comes to mind. There are lots of examples of both of these. Okay. So why are we studying these types of systems? Well, these are really good examples of what happens in our environment. We have dynamic systems that react to the changes that we supply as input. These are found in nature. They are actually real systems. We use the dynamical systems, differential equations, groups of differential equations that are intercoupled, that's what a dynamical system is, to be able to model these things. Let's go ahead and write that definition down. So, a dynamical system a little bit of a joke in math that this is kind of incorrect English-wise, dynamical system, but this is not the same as a dynamic system. It's a group of differential equations. So a group of intercoupled, interrelated differential equations. Okay, well, we use these to model the dynamic systems that we were just talking about, the ones that react to a change in input. Okay, all right, so just know that a while ago I mentioned that we only deal with linear systems, and especially that subset LTI systems out of linear systems. So we were just talking about nonlinear control and then linear control, and this is where we are right here, LTI systems. So what if something is nonlinear? What do we do? Well, we won't go too far into this, but there are techniques that we can do within certain bounds. We can linearize. We can use that linearization. It works within an isolated range. It may be fairly accurate within an isolated range. So we're going to say if the system is nonlinear. We might be able to use this. There's also Laplace transforms. We might be able to use that to simplify the analysis. And in that case, we want to use Laplace transforms to get away from things like convolution or very involved integration, derivation. It's much easier when you're in the S domain because then you have division and multiplication as opposed to the integration and actual derivation, convolution, those kinds of things. Okay, all right, so I do want to mention, because we're talking about robots and robotics is in the name of this class, that robots are basically just controlled machines. This course will teach you how to deal with problems, how to solve for the best solution for a linear feedback control, how to deal with the disturbances, set point, track a signal, all of those kinds of things. Those can be used within robots. So we are not actually building a robot, but we are studying the building blocks which would be necessary in order to build a robot, perhaps. Okay, it isn't exactly a course in robotics, but it's an introduction to some of the basic steps that you would use in robotics, if that makes sense. Okay, All right, so this actually is a really good course to take before you go into that kind of thing. And I would encourage you to look at the links that I'll leave on Canvas for you. Basically just to enjoy robots and all the technology that's out there. Okay, I do want to go through a really quick kind of overview of the history of control. Okay, so we can kind of show where we came from and where we are. Before we go through that, what kind of control are we dealing with? There are two major subsets in terms of time. There is, so if we talk about types first, there is the continuous. And we think about continuous in terms of like the analog world. We are going to be dealing with continuous control in this course. So this is us. I'll put a star by everything that's us. There's also discrete. Now, if you're thinking like, hey, I'm dealing with MATLAB, I'm dealing with a computer, isn't that actually discrete? Well, yes, but the sample time is going to be so small that it'll appear continuous. But that's a really good question. Okay. So discrete kind of deals with samples. There are different kinds of discrete methodology. There are ways that you can either hold your sample or let it vary according to some predetermined algorithm. Okay. All right, so essentially we are always measuring here. Control is always active. Okay, and if we're dealing with samples for discrete, then we can only act at predetermined times. Okay, so say if we are dealing with a discrete control or we're dealing with a discrete system, we can only make control decisions when we get that sample data. So we get that sample, we can make a decision, and so forth. Okay, but these are the two main types. Okay, all right, so there are two major worlds out of control. We can separate it into. One is classical, and one is modern. So we kind of borrow from both of these in this course. I'm definitely going to mention modern techniques. Some of the techniques that we are dealing with are also classical, so I'm going to put a star by both of these. All right, the characterization of both of these. Classical, it's more around dynamic system modeling, feedback, closed loop, kind of control. PID controllers, that is proportional integral derivative types of controllers. They use a piece of each one of those things. Use of transfer functions and things like that. So those are all things that we will be mentioning or using a lot of this semester. So I will go ahead and list these things. So we already talked about how we are going to be modeling dynamic systems. Using feedback, of course. Closed loop systems. I will mention PID controllers. We'll actually design controls that fit within this type. And then we'll also use transfer functions. At the very end of the course, we will be doing a lot of frequency domain analysis. Okay. All right, so for modern control, the thing that really characterizes modern control is the Kalman filter. I don't go into the Kalman filter. That's really more of the second course in this sequence. 486 deals a lot more of that, but we will mention state space, particularly when we deal with the math flow diagrams when we're drawing out our systems with block diagrams. Also, disturbance accommodating control, DAC, disturbance utilizing control, discrete continuous, which I mentioned my thesis was in, remember? And there are many others. They all fall within the modern control area. Okay. Now, if we were to talk about system-wise, again, we can split things into two main camps. So we're talking about control areas here. We are talking about the systems here. We have both linear and nonlinear. So we know that we are in linear area, so I'll put the star by here. And then we also have nonlinear. So what characterizes linear? Well, the use of superposition. That applies to these systems. Okay, we can also use linear differential equations for modeling. And then we are also, remember, within that subset LTI systems, we have LTI systems, linear, time invariant. We can use frequency domain analysis using Laplace, Fourier, Bode plots, Nyquist, and root locus. Those are all things that we will deal with later on. So I'm going to go ahead and list those as well. So Fourier, Laplace, Bode plots, and root locus. Oh, and actually also Nyquist. And there are some alternatives to Nyquist as well. Since we're in North America, Nyquist is taught more over here, but in Europe, there are different techniques that they prefer over Nyquist. At least from what I've heard, what I've read. Okay. Nonlinear control. Oh, by the way, all of those techniques are also in your text, no matter what version you have. You get both techniques. Nonlinear. What characterizes this? Well, we can't use superposition. It is in the case of no superposition necessarily. So it's not guaranteed. Because remember, a linear system falls within the whole bucket of nonlinear. Okay, so no superposition necessarily. These are more real-world problems. Okay, they can be modeled by nonlinear differential equations. And then we would use techniques like with limit cycles. I'm going to say this wrong, but Poincare maps. Don't know how to say that. It's a French word. Lyapunov stability analysis. probably said that wrong too. That is a, I believe, Russian word. And things like describing functions and linearization, which we've already mentioned, and perturbations. And I'll just write that real small down here. And describing functions. Okay. Those are techniques. We won't go into any of these, but they are worth mentioning. Techniques exist for dealing with nonlinear systems. And if you're interested, you can always look up these. Or if you take a course in nonlinear differential equations, you will definitely come across at least limit cycles and probably some of these other techniques. Okay, we've already talked about CISO and MIMO. Note that you can have more than one loop, more than one process in a system. You can have more than one input, more than one output. Having more than one input does not necessarily mean you have to have more than one output. You can have any number of inputs, any number of outputs. They don't have to be related. Okay, we were about to talk about the history of control. So one more thing right before we get into that, I just want to mention, because there are a number of classical problems that are solved, and it kind of goes into the history a bit. Okay, so classic controls problems. If you are looking for a new control technique, you are learning about something new, then one of these will probably have been solved. Essentially the first one I'm talking about, that is the blood glucose problem. So I remember seeing a presentation on sliding mode control. That's something that they use with the lunar lander. And it's a type of nonlinear control, and they were solving the blood glucose problem. Essentially, you design a device, and it is a control device, and it monitors a glucose level in the blood of a patient that is a type 1, type 2 diabetes type of patient, and it releases insulin based on measurements. So, very cool problem. Other ones that keep coming up, of course, I have mentioned thermostats several times already in this lecture, and of course, navigational problems. And that can be either missile, rocket, and do please forgive me if I make a misspelling. Sometimes I don't see it until well after, and I just feel like I might have misspelled missile there. Hopefully not, but we'll see. Missile, rocket, or things like a helicopter or car. Navigational kind of things. And then, of course, flight would be a part of that. And then also things within like hardware, like spin disks or disk speed. Maximizing hardware, essentially. And then, of course, this one is my favorite, automation. Automating the boring stuff. Okay, so that's classical problems that you might come across, and some of these are really interesting to kind of like set in your mind. When we're talking about controls, designing controls, that this would be something you could apply to directly. All right, so now to the history. All right, so the first control kind of implementation that we have on record, there are actually kind of two of them. Greek water clock, and that is mentioned in your book. Actually, probably a lot of these are mentioned in your book. And that happened somewhere around 300 BC. where they had a clock based on water levels and dripping of water. There is also evidence of an oil lamp, same kind of thing, oil levels, and that was said to be around 250 BC. So one or both of these are kind of really early on. First evidence we have of feedback usage occurs somewhere around 1600 in Europe. The application of that was steam power. Okay. First time we have automatic feedback. It's in about 1769, again with steam power, and this was with speed regulation. Okay, and then we jump to around 1765 in Russia. We have feedback water regulation in a broiler. Okay, around 1868, Maxwell, who, if you're an EE student, you know Maxwell very well. You love his math, love his equations. Very important to your work. Okay, so he used math for expressing control theory using differential equations. So that was a huge step in the direction that we have today. And then we have World War II. So World War II affected control theory quite a lot. We had two big components out of that, Bell Labs. And Dr. Johnson would always say that, and you'll hear me mention him quite a bit. I took this class from him, and there was a lot of really neat things that he would say, and I'd always try and remember. All the good things came from Bell Labs. Not exclusively, but a lot of good things, that is. So Bell Labs gave us, from Harold Black, expression of the stability of systems using frequency analysis. So that's going to be the second half of this course. And also negative feedback. Okay. All right. We also got from that, so I'm going to go ahead and continue on the next page. We also had Richard Bellman, very big name in control. Good one to know. He gave us dynamic programming. Richard Bellman gave us a lot of things. He has a lot of papers out there. Very good person to study. And then the other person I want to mention is Harry Nyquist, along with Hendrik Wade Bodie. Okay, so from them, we have the Nyquist stability criterion, and then we also have the Bodie analysis. So you can recognize their last names from topics that we're going to study. To me, it's a little funny because, of course, probably like many of you, you hear Bodhi plot first, and when you hear, oh, there was actually a guy named Bodhi, it's a little funny. Yeah. But if we jump back to our timeline, 1960s, we have Kalman. So Rudolf E. Kalman is also a really good guy to study. He's really interesting. He's contributed so much. Namely the Kalman filter. That is probably the #1 reference thing out of control theory. So that is named for him. Rudolf E. Kalman out of MIT. And that was published in 1960 to 61, and it's also referenced as the Kalman-Bucy filter. He published this with another scientist, and they both contributed to it. Okay. 1970s, we then have the emergence of optimal control. Okay, so from this point on, we are in modern control territory. And of course, this list that I'm writing is not exhaustive. There are so many different kinds of control out there. I am hitting the big ones that you might encounter a course from. We then have sliding mode. That emerged in the 1980s. This is Dr. Stessel's area of expertise. And again, like I mentioned, it is used in a lot of space applications, especially in the lunar lander. I believe in the moon buggies. I'm not totally sure about that, but it is a nonlinear technique. So that's his area of specialty. Okay, so I do want to put in here, because I am teaching the course, and because I have an affinity for this type of control, discrete continuous control was first published, it first emerged in 1982, and that is one of Dr. C.D. Johnson, that is one of his areas of expertise. And so this was first formulated at UAH. It is a UAH contribution. Dr. Johnson, as a note, he also worked heavily in disturbance utilizing and disturbance accommodating control. Okay, that is not where control ends. These are major fields. Okay, there has been a lot of work done since then as well. And if you want to look in IEEE and read up on that, you can find many publications from Dr. Stessel and Dr. Johnson, as well as many other students, PhD students and master's students from UAH, as well as other places as well. Okay, Bell Labs and MIT gave us a whole bunch of stuff, so at this point, we've gone through. This is a lot of the definitions and the history and kind of the conceptual, conceptual information to kind of get started with the course. So, one thing I really like about this course, just as we're talking about it, we get to use math. We get to use a lot of math, and it's not obtrusive. It's not too abstract. Even when we're dealing with symbolic equations. We will typically deal with an ordinary differential equation in terms, and I'm just going to write this out so I can point things out to you. Something that, let's say, looks like this. We're going to put a 0 on this side. These will vary with time, so they'll be of t. All right, so in this course with the symbolics that we use, this is a course equivalent to the second derivative of y. So if we were to talk about dy squared dt squared. That would be equivalent to, say, a y dash dash. You may be familiar with that. That is, of course, equivalent to y dot dot. Okay, this is kind of a controls nomenclature. This may be new to you, but that's the formulation that we like to use. We will formulate systems in this kind of a look, differential equations, and then we will be solving for a control. At least in the first half of this course, this is what we'll be doing. Okay, we'll be designing a control, assuming different algorithm. Say I might give it k1y plus a k2y dot, and then I would plug this in here. So this is the direction that we're going. Okay. Before we get to designing a control or talking about what a control algorithm should contain, we're going to talk about stability. We're going to talk about characterizing the system. So that's what's coming up next. So we will be approaching that in the next lecture. But for now, thank you for joining me, and I will see you next time.